In this video, we're going to talk about some common concepts that are typically taught in the second semester of physics. So let's go over charges. Now you know that like charges, such as two positive charges, will repel each other. They will feel a force that will push them away from each other. Whereas opposite charges, they attract each other. So if you have a positive charge and a negative charge, these two will feel a force of attraction. And you could quantify this force using Coulomb's law. And here it is. So the electrostatic force between two charges is equal to K times Q1 times Q2 divided by R squared. Now K is a constant. It's equal to 9 times 10 to the 9, and the units are newtons times square meters per Coulomb square. So that's just a fixed value. Now Q represents the electric charge, and Q is measured in coulombs. R is the distance between the charges. And now let's think about what this equation tells us. If we were to increase the magnitude of, let's call this Q1 and Q2. So let's say Q2 increased from 100 microcoulombs to 200 microcoulombs. What do you think the magnitude of the force will be between the two charges? If you increase the magnitude of the charge, the electrostatic force between the charges will increase. In fact, if you double Q2, then F will double in value. If you double Q1, F will double in value as well. If you double both Q1 and Q2, F will increase by a factor of 4 because 2 times 2 is 4. Now, what happens if you increase the distance between the two charges? So let's say here's charge 1 and here is charge 2. And let's say the force that's acting on each charge is 100 newtons when the distance between them is 1 meter. What's going to happen if we double the distance between the two charges while the magnitude of the charge is still the same? So now the separation distance is 2 meters. Will the electrostatic force acting on the charges, will it increase or decrease? Well, because the charges are further away from each other, we expect that the force that's acting on them will be weaker. And so anytime you increase the separation distance, the electrostatic force acting on these charges will decrease. You can liken this to a relationship. When you're close to each other, the bond is stronger. But when you're further away, the bond is weaker. And the same is true for charges. Whenever you have two electric charges that are very close in distance to each other, the forces acting on those charges will be strong. Whereas if they're far apart from each other, the forces acting on them will be weak. Now, if we double the distance, what's going to happen to the magnitude of the force? So using Coulomb's law, here's what you can do. For these types of questions, for any variable that doesn't change or any constant that doesn't change, replace it with a 1, except for the one that changes. So K, Q1, and Q2 are not changing in this case, so I'm going to replace it with a 1. Now the distance increased by a factor of 2, and so I'm going to replace R with 2. But because R is squared, I need to square the 2, and 2 squared is 4. So the force is going to be 1/4 of what it was before. 1/4 of 100 is 25. So now the force acting on each charge is 25 newtons. Now let's say we have a positive charge and a negative charge separated from each other by a distance of 3 meters. We'll call this Q1 and Q2. Now let's say the force acting on each charge is 500 newtons. So what's going to happen between the forces acting on those charges if we bring the charges closer to each other? So let's say the separation distance is now 1 meter instead of 3 meters. So we reduce the distance by a factor of 3. And at the same time, let's double the magnitude of charge 1 and let's triple the magnitude on charge 2. So by what factor will the force increase by? So using Coulomb's law, F is equal to K Q1 Q2 over R squared. The best way to get the answer is to replace everything with the amount that we changed it by. Now K is the same, so let's replace that with a 1. Charge 1, we doubled it. It went from 1 Q1 to 2 Q1. So we doubled Q1. We tripled Q2. And R was reduced by a factor of 3. So it's 1/3 of its original value, and we need to square it. So 2 times 3 is 6. 1 over 3 squared. 1 squared is 1. 3 squared is 9. So this is 6 divided by 1 over 9. Let's multiply the top and the bottom by 9. 6 times 9 is 54. 1 over 9 times 9 is 1. The 9's cancel. So the force will increase by a factor of 54. Now the original force was 500. So the new force acting on these two charges is going to be 500 times 54, which is 27,000 newtons. So to review, make sure you understand this between charges. If you increase the magnitude of the charge, the electrostatic force acting on them will increase. If you decrease the distance, the electrostatic force will increase. Now let's work on a simple math problem relating to Coulomb's law. So let's say that Q1 has a magnitude of 200 microcoulombs and Q2 has a magnitude of 300 microcoulombs. Now let's say the separation distance between the two charges is 80 centimeters. Calculate the magnitude of the force between them. So we could use this equation. F is equal to K Q1 Q2 over R squared. Feel free to pause the video and try this. So K is 9 times 10 to the 9. Q1 is in microcoulombs. Micro is 10 to the negative 6. So 200 microcoulombs is going to be 200 times 10 to the minus 6 coulombs. Now for Q2, we don't have to worry about the negative sign because if you're looking for the magnitude of the force, it's always going to be a positive number. The only thing we need to worry about is the direction. The direction of the force acting on Q1 is going to be towards the negative charge, and the direction of the force acting on Q2 is going to be towards the positive charge. So when dealing with opposite charges, you're going to have a force of attraction. When dealing with like charges, like 2 positive charges or 2 negative charges, you're going to deal with a force of repulsion. So Q2, we're going to replace it with 300 times 10 to the minus 6 coulombs. Now the distance between the two charges is 80 centimeters. 1 centimeter is 10 to the minus 2 meters. And so you can write 80 times 10 to the minus 2 meters, and then we need to square it. So let's go ahead and plug in this whole thing. So you should get 843.75 newtons as the electrostatic force acting on these two charges. That's the answer. Now you might be wondering what is meant by electric charge. You heard of that term before and you have an idea of what it is, but what really is electric charge? Q, the symbol for electric charge, represents the quantity of charge. When Q is negative, what this means is that you have more electrons than protons. And when Q is positive, there are more protons than electrons. The charge of one electron is equal to negative 1.6 times 10 to the negative 19 coulombs. The charge of one proton is positive 1.6 times 10 to the negative 19 coulombs. So let's say if we have a charge of positive 100 microcoulombs. What does that mean in terms of protons and electrons? So using this conversion factor, one proton has a charge of positive 1.6 times 10 to the negative 19 coulombs. We can determine the number of excess protons that represent this charge. So let's say if we have a piece of metal with a charge of positive 100 microcoulombs, there's more protons than electrons in this object. Now to quantify it, we're going to convert coulombs to protons. 100 microcoulombs is 100 times 10 to the negative 6 coulombs. And we know that one proton has a charge of 1.6 times 10 to the negative 19 coulombs. Make sure you set it up in such a way that the unit coulombs will cancel. So now let's divide 100 times 10 to the minus 6 by 1.6 times 10 to the negative 19. And so the answer is positive 6.25 times 10 to the 14 protons. So what this means is that there's this many protons more than electrons. This doesn't tell you how many protons are in the object or in the metal. It simply tells you how many protons or how many excess protons that you have relative to the number of electrons. Because in the metal, you're going to have both electrons and protons. So let's say if there were 1.5 times 10 to the 14 electrons, and the object still have a net charge of positive 100 microcoulombs. How many protons will there be? So this number is the difference between the number of protons and electrons. It just means we have that many more protons than electrons. All we need to do to get the answer is we need to add these two numbers because there's going to be more protons than electrons. So 1 plus 6 is 7, and 0.5 plus 0.25 is 0.75. So we're going to have 7.75 times 10 to the 14 protons. And so that's how many protons would actually be present in that object, given this charge. So that's how you could find the answer. Now let's say if you have an object with 4.8 times 10 to the 16 electrons, and it has, let's say, 2.5 times 10 to the 16 protons. So what is the net charge in this object? What would you do to find the answer? Now there's a simple formula that can help you to calculate the answer. The net electric charge, you could use lowercase q, or sometimes capital Q will be used for that. So the net electric charge is going to be the difference between the number of protons and electrons times the individual charge of a proton or an electron. That is the absolute value of that charge. And so that's all you got to do. So in this case, we have 2.5 times 10 to the 16 protons, and we have 4.8 times 10 to the 16 electrons. Let's multiply by this number. So 2.5 minus 4.8, that's negative 2.3. And it makes sense why it should be negative, because we have more electrons than protons, and so Q has to be equal to a negative number. Now, if we multiply these two numbers, this will give us negative 3.68 times 10 to the minus 3 coulombs. Now, 10 to the minus 3 is associated with the prefix milli. So we could say that this is negative 3.68 millicoulombs. And so we can write the final answer like this. So as you can see, if you have more electrons than protons, the net charge will be negative. Now let's go back to electric forces, because sometimes you'll be given a situation where you have multiple charges, like this one. Now let's focus on the concept more than the math associated with these types of problems. Let's call this Q1, Q2, and Q3. And here is the question. What is the direction of the net electric force acting on Q2? Is it this way? Is it that way? Is it going north? Is it going south, east? What is the direction of the net electric force? Now let's say that each charge has the same magnitude and all of the charges are equidistant from each other. So let's say Q1 and Q2, they're 1 meter apart, and Q2 and Q3 are also 1 meter apart. Now, focusing on Q2, Q2 is attracted to Q1, and so it feels a force that pulls it to the left. Q2 is also attracted to Q3. It feels a force that pushes it down. And so if you combine these two vectors, if you go to the west and also south, the resultant force vector will be directed southwest. And so at this instant of time, Q2 is going to feel a force that's going to pull it in this general direction. Now let's try another problem. So let's say that this time we have 3 positive charges. We'll call it Q1, Q2, and Q3. What is the direction of the net electric force acting on Q1? Let's say, just like before, the charges have the same magnitude and they're equally spaced apart. What is the direction of the force acting on Q1, or approximate the direction? Now, Q1 is repelled by Q2. So Q2 causes Q1 to move in this direction. Let's say the distance here is 1 meter, and the distance here is 1 meter. Now the distance between Q1 and Q3 will be more or greater than 1 meter based on the Pythagorean theorem. So if you basically use C squared equals A squared plus B squared, if you take the square root of 1 squared plus 1 squared, you're going to get the square root of 2, which is about 1.4. And so because the distance between Q1 and Q3 is greater than that between Q1 and Q2, the force that is exerted on Q1 by Q3 is going to be weaker than this force. But this force will be in this direction, but we should draw a smaller vector. So I'm just going to make that vector smaller. Now, if we were to combine these two vectors, what would we get? One way to add vectors graphically is to draw them from head to tail. So if we draw the first vector, which is going to be longer, let's call this F2 because it was based on charge 2. We'll call this F3. And then the second vector, which is going in this general direction, but it's shorter. And then starting from the original position to the final position, this would be the resultant vector. We'll call it FR. So it looks something like this. So that's going to be approximately the direction of the resultant electric force acting on Q1. And so that is our answer. Now let's talk about something known as the electric field. This is the next topic beyond electric force. So what is the electric field? The electric field is defined as the force exerted on a positive test charge divided by the magnitude of that test charge. And so here's the formula for the electric field. It's equal to force divided by charge. So let's say if we have a positive charge, and let's say this positive charge has a magnitude of 50 microcoulombs, and it feels a force that pushes it towards the right. And let's say the magnitude of that force is 0.02 newtons. What is the electric field at that point in space? So using this formula, it's simply the force exerted on the charge divided by the magnitude of that charge. So it's 0.02 newtons divided by 50 times 10 to the minus 6 coulombs. So the electric field in this region of space, which the positive charge currently occupies, the electric field in that region is 400 newtons per coulomb. And so the electric field is basically the ratio between the force exerted on a charge divided by the magnitude of that charge. So think about what this number means. So this electric field tells us that at that point, it can exert a force of 400 newtons per every coulomb of charge. So if you have a charge of 1 coulomb, so let's say this is a positive charge of 1 coulomb, it will exert a force of 400 newtons. Now, if we double the magnitude of the charge, but the electric field is still the same, that is 400 newtons per coulomb, the force exerted on that charge will be 800. And so, as the magnitude of the charge increases, the force that's exerted on that charge by the electric field will increase. And so the electric field gives you a ratio between how much force will be exerted per unit of charge. So if we have, let's say, another positive charge with a charge of 5 coulombs, the force exerted on it will be 5 times 400, and so it's going to be 2,000 newtons. So let's say that we have an electric field vector that is directed east. What's going to happen if we place a positive charge in this electric field? And let's compare it if we place a negative charge in that same electric field. So what you need to know is that a positive charge will feel a force in the same direction as the electric field. A negative charge will feel a force that will accelerate it in the opposite direction of an electric field. So let's say if we have an electric field directed north. So go ahead and draw the direction of the electric force acting on these two charges. So the electric force acting on the positive charge will be directed north in the same direction as the electric field. For the negative charge, the electric force will be directed south, opposite to the direction of the electric field. Now, it's important to understand that every charge can create its own electric field. The electric field created by a positive charge emanates in all directions away from the positive charge. Now, the electric field created by a negative charge always points towards the negative charge. Now, why is this important to know? Sometimes you might be given a situation where you have multiple charges. Let's start with a simple situation. Let's say we have a positive charge and a negative charge. And we wish to determine the direction of the electric field at 3 points. Let's say at point A, at point B, which is at the midpoint between Q1 and Q2, and also at point C. What is the direction of the electric field at these points? Well, let's start with point B. So to determine the electric field exerted by Q1 at point B, draw a line from Q1 to point B. We'll call this E1 because it was created by Q1. Now, to draw the electric field vector created by Q2 at point B, remember, from a negative charge, the electric field created by it has to go towards the negative charge. So E2 will be a vector starting from point B, drawn to the negative charge. So it will be in this direction. So at point B, the net electric field will be directed east because it's the sum of these two vectors. Now let's focus on point A. The electric field at point A created by Q1 will be in this direction. So this is going to be E1. So you need to draw it from the positive charge to the point. So remember, the electric field created by any positive charge always emanates away from the positive charge. Now the electric field created by Q2 at point A, because it's a negative charge, we need to draw it from the point pointing towards the negative charge. Now this vector is going to be smaller than E1. And the reason why E2 is smaller than E1 is because Q2 is further away from point A than Q1 is. Because Q1 is closer, the electric field created by Q1 is going to be stronger than Q2. So here's the formula for the electric field created by a charge. It's KQ over R squared. As you increase the magnitude of the charge, the electric field increases. As you increase the distance, the electric field decreases. And that's why E2 is less than E1 at point A, is because the distance between Q2 and A is greater than the distance between Q1 and A. And so that's why E1 is stronger, but E2 is weaker. So the net electric field at point A is going to be directed west as opposed to east because E1 is greater than E2. Now at point C, to draw E1 is going to emanate away from the positive charge towards point C. So it's going to be going in this direction. And for E2, it's going to point towards towards Q2, that is towards the negative charge. And it's going to be bigger because point C is closer to Q2 than it is to Q1. So this time, E2 is greater than E1. And so the net electric field will be directed west again because this vector is bigger than this one. And so that's how you could determine the net electric field at a certain point if you have multiple charges. Now, let's say if we have a positive charge in this region and a negative charge here. And so let's call this Q1 and Q2. What is the direction of the net electric field acting at point A? So feel free to pause the video, draw the vectors, and determine the net electric field vector at point A. So Q1 is going to exert an electric field in this direction towards point A. Q2 is going to exert an electric field toward itself from point A in this direction. So if we add those two vectors, the resultant vector, so we have E1 going in this direction and then E2, so the resultant vector is here. So this is where we started and this is where we finished. So at point A, the net electric field is going in this direction. So it's going in a northeast direction. Let's try another problem. So let's say we have 3 charges. Let's say Q1, Q2, and Q3. And let's say that they're equally spaced apart. So let's say the distance between Q1 and Q2 is 1 meter, and the same is true between Q2 and Q3. What is the net electric field at point A? What is the direction of the net electric field at that point? So Q1 is going to exert an electric field away from itself towards point A, and the same is true for Q2. Positive charges always direct an electric field away from them, and the electric field will always point toward the negative charge. And so these are the 3 vectors that we have. And all the charges have the same magnitude, and so E1 and E3, they're going to be the same length. However, E2 should actually be the biggest. In terms of distances, let's say that the distance between Q2 and A is 1 meter. This is going to be about 1.4 meters, and this is going to be 1.4 meters. So the electric field vectors for those two should be the same. But this one, because the distance is the shortest, it's going to have the greatest electric field. So E2 is greater than E1 in terms of magnitude, and E1 and E3, they have the same magnitude. So that's going to give us, let me just delete this first. That's going to give us a good idea of how long we should draw the relative vectors. So we said E2 is greater than E1, and E1 is equal to E3. So we're going to say that E2 is about that long. E1 is going to have to be shorter, and E3 will also be shorter, but the same length as E1. So how can we add these 3 vectors so that we can get a general idea of the direction of the net electric field at point A? Now, what we need to do is break up E1 and E3 into its components. So E1 has a y component that is going in the negative y direction, and E2 has an x component that's going in the positive x direction. E3 has a y component going up and an x component going in that direction. Actually, I need to correct this. E3 should be going towards the negative charge. So correction. I had it before, but for some reason I had it pointing towards A. But the electric field created by a negative charge should always point towards a negative charge. So E1 still has a y component going in the negative y direction and a positive x component. Now E3 has a negative x component and a negative y component. Now because E1 and E3 are of the same magnitude, we could say that the x component of E1 and the y component, the x component of E3, they cancel because they're anti-parallel and they're the same length. So we could cancel those two. Now notice that the y components, they're parallel. They're going in the same direction. And so we can add those 2 y components to form a bigger vector going in the y direction, which I'm going to draw in blue. And now let's combine that with E2, which is going in this direction. And so the net electric field, if we combine these 2 vectors, or let's delete this one and just add it here, we can see that the net electric field is going to be in that direction. And so that's how you could determine the net electric field vector for this particular problem. Let's say if we have two charged metal plates. On the left side, this plate will be positively charged, and on the right side, this will be negatively charged. Now, what's going to happen if we place a positive charge near the positive plate? What's going to happen? Now, there is an electric field in between the two plates. We know the electric field emanates away from the positive plate and points towards the negative plate. If you recall, positive charges create an electric field that emanate away from them, and negative charges create an electric field that points towards them. So the net electric field in between these two plates is directed towards the negative plate. Now, the positive charge will feel a force that will accelerate it in the direction of the electric field. Now, this electric field, would you say it's doing positive work or negative work on the charge? Let's say the charge was initially at rest at point A, and it's moving to point B. In this case, the work done is positive. If you recall, work is equal to force times displacement. Because the charge is moving to the right, its displacement vector is towards the right. If the force and displacement vector are parallel, then the work done is positive. Because the work done is positive, the kinetic energy of the object is increasing. And also the fact that the object is speeding up. It's moving from rest and it's accelerating towards the right. So anytime the speed of an object increases, the kinetic energy increases. And if the kinetic energy increases, that means that the potential energy must be decreasing. Now, let's say if the positive charge is placed towards the middle or somewhere near the middle of the two plates. And let's say initially this charge is moving towards the left. Now, what can you say about the work done by the electric field on this charge? At this instant of time, as it moves initially to the left, the electric field still exerts a force that is parallel to itself. So the electric force acting on this charge is still directed towards the right. And it makes sense because the charge, the positive charge, is repelled by the positively charged plate, but it's attracted to the negatively charged plate. And so even though it's moving to the left, due to its initial momentum, it feels an electric force that is pulling it towards the right, towards the negatively charged plate, because opposite charges attract each other. And so right now, the charge has a displacement vector to the left, but the force is towards the right. And so because the force and the displacement vector are anti-parallel or opposite, based on this equation, work equals force times displacement, the work done on this charge by the electric field is negative. So what does that mean? If the work done is negative, that means that the kinetic energy is decreasing. If you recall from the work energy principle, work is equal to the change in kinetic energy. And when the kinetic energy goes up, the potential energy goes down. And if the kinetic energy goes down, the potential energy is going up. So the change in kinetic energy is equal to the negative change in potential energy. So in this case, this charge is losing kinetic energy. It's slowing down. However, its potential energy is increasing. Now, this situation is analogous to, let's say if we have a ball placed above the ground. At this point, above the ground, it has high potential energy, and the ground has low potential energy. And so as the ball falls from a position of high potential energy to low potential energy, we could say that its potential energy is decreasing, but it's speeding up as it falls to the ground, and so the kinetic energy is increasing. Now, this ball is falling down, so its displacement vector is negative. It's going in the negative y direction. But the gravitational force acting on this ball is also in the negative y direction. So because the force and the displacement vector are in the same direction, the work done on this object is positive. And anytime the kinetic energy is increasing, the work done on that object is positive. So if the change in KE is positive, the work done on that object will be positive. So this situation where the ball is falling towards the ground is analogous to this situation. Let's say if we have a positive plate at the top and a negative plate at the bottom. A positive plate has more potential energy than a negative plate. So this would have high potential energy, and this will have low potential energy. Now, in the case of the ball falling to the ground, at the top, it has high gravitational potential energy. But when dealing with charges, we need to say electric potential energy. Sometimes you'll see me write EPE for that. Now, as the positive charge, let's say if we place it at the top, as we know, it's going to accelerate towards the negatively charged plate. And so it's also moving in that direction, and it feels an electric force pulling it in that direction. And so just like the ball falling towards the ground, we know that the work is positive, that is the work being done on the positive charge and on the ball, and the kinetic energy is increasing because it's speeding up. And as it moves from high potential energy to low potential energy, the potential energy is decreasing. Now, we talked about another scenario where a positive charge was given an initial velocity towards the positively charged plate, but it still feels a force that accelerates it towards the negatively charged plate, because a positive charge will always feel a force in the same direction as the electric field. For negative charges, it's opposite to that. So in this case, we said that because the force and displacement vectors are antiparallel, the work done on this charge is negative. And as it goes up, but the force is trying to bring it down, it's slowing down. So the kinetic energy is decreasing, but the potential energy is increasing because it's moving towards a position of high potential energy. That is a position of high electric potential energy. Now, the same is true for the ball in this case. So imagine if you throw a ball upward in this direction. Actually, let me draw it here. So let's say the ball is going up. It has an initial upward velocity. Gravity is still acting on the force to bring it down. Now the ball, because it's moving up, it has an upward displacement vector. So because these two are opposite to each other, the work done on this ball is negative. As the ball moves towards a higher position, it's moving towards higher potential energy. So the potential energy of the ball is increasing. But as it goes up, it's slowing down, and eventually it's going to reverse and go back to the ground. So as it's going up, it's slowing down. Its kinetic energy is decreasing. And you can see the situation is the same here. And so by relating these two concepts, you can tell if a charge is if positive work is being done on a charge, or if negative work is being done on it, and if it's speeding up or slowing down. Now we need to visit something called electric potential. This is the next topic that you need to learn after electric field. So what is meant by the term electric potential? Electric potential, represented by the symbol V, is the ratio between the electric potential energy of a charge and the magnitude of the charge. The unit for electric potential V is the volt, and 1 volt is equal to 1 joule of potential energy, that is electric potential energy, per 1 coulomb of charge. And a good way to understand the concept of electric potential is using those two plates again. Now, it's important to understand that the difference in electric potential is really what can be measured, and so that's the important stuff. Electric potential itself is an arbitrary number. It's only useful if you compare it to the electric potential at another position. So let's say that the electric potential at the negatively charged plate, we're going to say it's 0 volts. And the electric potential at the positively charged plate, let's say it's 100 volts. Actually, let's say it's 5 volts. Now, let's say if we have a positive charge at position A. Let me move it close to this plate. So let's say it starts directly on the positively charged plate, which we'll call position A. And it accelerates towards the negatively charged plate. And let's say it's a 1 coulomb charge. So this 1 coulomb charge is moving through a potential difference of 5 volts, from 5 to 0. And we know that it's going to gain kinetic energy during this process, and it's going to lose potential energy. So in this case, now keep in mind 1 volt represents 1 joule per 1 coulomb of charge. So when a 1 coulomb charge moves through a potential difference of 5 volts, 5 joules of work is being done on that charge. Now, whether the work be positive or negative, it depends on the situation. Is it moving from A to B or B to A? Now we know that as it moves from A to B, the kinetic energy is increasing. So therefore, the electric field is doing 5 joules, that is positive 5 joules of work on this 1 coulomb charge. And so we could say that the charge loses 5 joules of potential energy during this process, or we could say that it gains 5 joules of kinetic energy. Now, let's compare it to another charge, but this time we're going to say this charge has 2 coulombs of charge, and it's moving from A to B. In this case, we could say that 10 joules of work will be performed on this 2 coulomb charge as it moves from A to B. And so we can also say that it's losing 10 joules of potential energy or gaining 10 joules of kinetic energy. Now, this leads us to an important equation. So the work done from moving a charge, let's say from B to A, is equal to negative Q times the electric potential difference between points A and B. So you could say it's equal to negative Q times VA minus VB. So let's say we have 2 charged plates again. But this time we're going to use an electron. And let's say the electron is initially at the positively charged plate. Now naturally it doesn't want to move towards the right. It's repelled by the negatively charged plate. But let's say we use an external force and force it in this direction. So this is not the force generated by the electric field. We're using an external force to move it, let's say from A to B. Let's say the potential at this plate is 0 and at this plate is 50. Now, let's say this is just a negative charge, not necessarily an electron, but there's many electrons. And so let's say the total charge of that object is 20 microcoulombs, but it's going to be negative though. How much work is done by moving a charge from A to B? And is the work positive or negative? So right now, the displacement of the negative charge is towards the right. The electric field is also towards the right. But a negative charge will feel an electric force that will accelerate it in the opposite direction of the electric field. So even though we're using an external force to move it from A to B, the negative charge still feels an electric force that will attract it or pull it towards the positive plate. Now, because the electric force and the displacement vector are anti-parallel, the work done by the electric force is negative. Now let's see if we can quantify this answer. Now we're going from A to B and not B to A, so this equation is going to change. So we're going to say the work done on the charge going from A to B is equal to, and I'm going to focus on this portion of the equation, negative Q times the electric potential difference between point B and point A. So VA is the electric potential at point A. VB is the electric potential at point B. But it's the difference in electric potential that really matters. And you know what? Let's change the charge. Instead of using micro, let's use a nice whole number. Let's say negative 4 coulombs. Now, if you recall, whenever a charge moves through, let's say, a potential difference of 1 volt, a 1 coulomb charge will have 1 joule of work done on it. It could be positive or negative, but it's going to be 1 joule of work. In this case, we have a 4 microcoulomb charge moving through a potential difference, so let me write delta V, of 50 volts. And so in this case, it should be about 200, because a potential difference of 50 volts means that the charge can gain or lose 50 joules of energy per 1 coulomb of charge. So it can gain 200 joules of energy or lose 200 joules of energy per 4 coulombs of charge. So using this formula, we have negative Q. Now Q is negative 4 coulombs because we're dealing with a negatively charged particle or object. And VB, the potential at point B is it's 0. The potential at point A is 50. So we have two negative signs. A negative times a negative is a positive. And 0 minus 50 is negative 50. So overall, this is going to be negative. So it's negative 200 joules of work being done on this negative charge. And so just as we predicted, the work was going to be negative when the negative charge moves from position A to B. So hopefully this section gave you a good understanding of the concept of electric potential energy and electric potential. So make sure you understand the difference. V represents electric potential without the word energy in it, just potential. And the unit for electric potential is the volt. So when you think of a 9-volt battery, what this tells you is that it can do 9 joules of work when it passes 1 coulomb of charge through a circuit. And so it helps you to understand the concept of voltage. Voltage is really the difference in electric potential. It's the change in the electric potential. So it's like VA minus VB or VB minus VA. So electric potential is simply an arbitrary number. It's simply V. But delta V, that is a voltage, which is more commonly used in everyday applications. So make sure you understand the difference between electric potential and voltage, and also electric potential energy, which is PE. So remember, 1 volt or electric potential is the ratio between electric potential energy and charge. And the work done by a charge or on a charge is negative Q delta V. And that is as the charge moves through an electric field or through an electric potential difference. Now, earlier in this video, we defined the electric field to be the electric force that is exerted on a positive tiny test charge divided by the magnitude of that charge. The electric field can also be calculated this way. It is the voltage or the potential difference between two plates, two charged plates, divided by the distance between them. So for instance, let's say if we have a positively charged plate on the right and a negatively charged plate on the left. And let's say this is assigned a potential of 0 volts. And this is assigned a potential of 50 volts. And the two plates are separated by a distance of 10 centimeters or 0.1 meters. What is the strength of or what is the magnitude of the electric field between the two plates? Now, we know the electric field will be directed towards the left, away from the positively charged plate, but towards the negatively charged plate. And using this formula, I put 50 meters. This is supposed to be 50 volts. Let me change that. The electric field will be the voltage between the two plates, and that is the difference between the potentials. So it's going to be a voltage of 50 volts divided by a separation distance of 0.1 meters. And so it's going to be 500 volts per meter. So the electric field, in this case, tells us how the electric potential changes per meter. So every meter is going to change by 500 volts, but the separation distance is only 0.1 meters. So here is another example. Let's say that's the positively charged plate, and here is the negatively charged plate. And let's say the potential difference between these two plates is 100 volts. And we're going to say the separation distance is 10 meters. So this is at 0 meters, this is at 10 meters. In the middle is 5. And let's say here it's 1 meter. And here it's 9 meters. Now the electric potential, not the electric potential, but the strength of the electric field is going to be the voltage divided by the separation distance. So the voltage, as we said before, which is the difference in the electric potential between the two plates, that's 100 volts, divided by a separation distance of 10 meters. And so 100 divided by 10 is 10. So what this means is that the potential should change by 10 volts every meter. And so 1 meter above the negatively charged plate, the potential should be 10 volts. 5 meters above the negatively charged plate, the potential should be 50 volts. 9 meters above the negatively charged plate, it should be 90 volts. So as you move by 1 meter along this vertical line, the potential should change by 10 volts because that's the electric field. It's 10 volts per meter, which you can also describe it as 10 newtons per coulomb. And so what we have is a potential gradient. And so let's say at 7 meters, if we wish to find a potential with respect to the negatively charged plate, it's going to be 70 volts higher than the negatively charged plate, but it's 30 volts lower than the positively charged plate. And so hopefully this helps you to understand the concept between the electric field and the potential in that field as it changes when you move by a certain distance. Now notice that the electric potential decreases as you move in the direction of the electric field. So keep that in mind. Now here's a question for you. Let's say we have an electric field vector that points towards the right. And let's say this is position A and position B. And the electric field, we're going to say it's 300 volts per meter. And let's also add position C. And let's say position A is our reference point, that's 0 meters. And C is 2 meters to the right of position. Actually, let's say C is the reference point. Let's say A is 3 meters to the left of position C, and B, we're going to say it's 5 meters to the right of position C. Now, let's say position C has a potential of 1,000 volts. What is the potential at A and what is the potential at B? Now, the electric field tells us that the potential changes by 300 volts every meter. So in 5 meters, it's going to change by 300 volts per meter times 5 meters, which is 1,500 volts. Now, is it going to be higher or lower than position C? Now remember, the electric field tells you how the potential is changing. As we move in the direction of the electric field, the electric potential is decreasing. So we're going from a high electric potential value to a low electric potential value. So that means that position B has a lower voltage, or rather a lower electric potential than position C. So as we move 5 meters to the right, it's just going to change by 1,500 volts. So this is going to be negative 500 volts because 1,000 minus 1,500 is negative 500. Now going to the left, we have a separation distance of 3 meters. 300 volts per meter times 3 meters, that's 900 volts. But going to the left, we're going towards a higher potential. So position A is 900 volts higher than position C. So this is going to be at 1900 volts. So as this example illustrated, you could see that the magnitude of the electric field can help you to determine how much the electric potential will change as you move a certain distance. And the direction of the electric field vector can tell you if the electric potential is going to decrease as you move to the left or as you move to the right. So remember, the electric potential decreases as you move in the direction of the electric field. If you move in the direction opposite to the electric field, the electric potential will increase. Now, just as a point charge can create its own electric field, a point charge can also create an electric potential at some distance away from itself. So let's say we have a positive charge with a magnitude of 100 microcoulombs. And let's say we wish to calculate the electric potential at a distance of 1 meter and also, let's say, at a distance of 10 meters. Let's call this point A and point B. To calculate the electric potential generated by a charge, you could use this formula. V is equal to K Q divided by R. So the electric potential at, let's say, point A is going to be the K value, which is 9 times 10 to the 9, times Q, which is 100 microcoulombs, or 100 times 10 to the minus 6 coulombs, and the distance between the charge and point A, which is 1 meter. Let's call this RA, the distance between the charge and point A. Now, if we plug in these numbers, this will give us a very big number of 900,000 volts, which is 900 kilovolts. 1 kilovolt is 1,000 volts. So that's the potential at point A. Now at point B, we expect that it's going to be much less than at point A because it's further away from the charge. As you move away from a positive charge, the electric potential will decrease. And so using the same formula, VB is going to be KQ over RB. So that's 9 times 10 to the 9 times Q, which is 100 times 10 to the minus 6, divided by RB, which is 10 meters. So the answer is going to be very similar, just 10 times less. So this is going to be 90 kilovolts. So as you can see, as you move away from the charge, as the distance increases, the electric potential decreases proportionally. So as we increase the distance by a factor of 10, the electric potential reduced by a factor of 10. Let's move on our discussion to capacitors. What is a capacitor? A capacitor is a device that stores electric charge, and it's made up of two metal plates separated by an insulator. The insulating material, known as the dielectric, can be air, it could be water, it could be paper, or any one of these things. Now, let's apply a voltage to this capacitor. The long side represents the positive terminal of the battery, and the short side represents the negative terminal of a battery. And so let's say we're applying a 12-volt battery to this capacitor. At this moment, the capacitor is charging. And so what happens is that electrons are being pulled from the plate on the left, and it's going to flow through this circuit, and the electrons are being deposited on the plate on the right. And so the voltage that's applied to the capacitor causes the electrons to flow from one side, and it pumps it to the other side. Now, because electrons are leaving the plate on the left, this plate becomes positively charged because it's electron deficient. There are more protons than electrons in that material at that moment. Now, for the plate on the right side, it has an excess of electrons. There's more electrons than protons, and so it acquires a negative charge. So this is the process by which a capacitor can be charged. So right now, it's in charging mode. The battery pumps electrons from one side to the other side of the capacitor. So as you can see, electricity can flow in the wires connecting the capacitor and the battery, but no electricity flows in between the capacitor. Now, once the capacitor is fully charged or fully discharged, then no current will flow in the wires. But while it's charging or while it's discharging, electricity can flow in the wires connecting the capacitor, but not between the plates of a capacitor. So be careful with that. Now, when the capacitor is charged, it acquires a charge of positive Q on the positive plate and negative Q on the negative plate. Now, these two values have to be the same. The only difference is the sign has to be opposite to each other. So as this plate gains a charge of positive Q, this has to gain the opposite charge of negative Q. It's just how the math works. Now let's talk about a capacitor being discharged. So let's say we take this capacitor and disconnect it from a battery, but connect it to, let's say, a light bulb. And let's say this capacitor has enough energy to power the light bulb. So at this point, we're consuming energy from the capacitor. So we say that it's discharging. It's giving away its energy. Now the electrons in this circuit will flow from the negatively charged plate to the positively charged plate until the charges become zero. So this is going to continue to happen until the charge goes from positive Q to zero. While this is happening, this is going to change from a negative Q to zero. And so everything is going to return to a state of equilibrium. Now, as the electrons flow in a circuit, energy will be transferred from the capacitor to the charges, which will eventually go into turning the light bulb on. So the electric energy provided by the charges is being transformed to light energy and thermal energy. Now let's focus on Q, the charge stored on a capacitor. So here's a formula that you need to be familiar with. Q is equal to CV. Q represents the electric charge stored in a capacitor. C is the capacitance, which is unique to each capacitor, and V represents the voltage across the capacitor. Now you could write delta V to represent the voltage, but typically this equation is presented in this form, and it's understood that V is not the electric potential on a single plate, but really the voltage across the two plates. So sometimes when you see V, it might represent voltage instead of electric potential, but if you see delta V, it certainly represents voltage. Now we talked about the unit for voltage, which is the volt, and the unit for charge, which is coulombs. Now the unit for capacitance is the farad, F-A-R-A-D. Now if we rearrange this equation and solve for C, C is equal to Q divided by V. So we could say that a 1 farad capacitor stores 1 coulomb of charge when 1 volt is applied across it. If we apply a voltage of 5 volts across it, it can store 5 coulombs of charge. Now let's compare this to a 10 farad capacitor. So a 10 farad capacitor can store 10 coulombs of charge per 1 volt applied to it. So notice the difference. If we have a 1 farad capacitor and we apply a 1 volt battery across it, it can only store 1 coulomb of charge. But if we have a 10 farad capacitor and if we apply the same 1 volt battery to it, instead of storing 1 coulomb of charge, we can store 10 coulombs of charge. And so the capacitance tells you how much charge can be stored in a capacitor per 1 volt applied to it. Now, we can increase the amount of charge stored on a given capacitor by increasing the voltage applied to it. For instance, if we increase the voltage to 5 volts, we can store 50 coulombs of charge. If we increase the applied voltage to 12 volts, we can store 120 coulombs of charge. And so, if you wish to store more charge on a capacitor, there's 2 ways you can do this. You can do this by increasing the capacitance, which is based on the physical characteristics of the capacitor, or by increasing the voltage applied to the capacitor. So increasing any one of these variables will lead to an increase in the amount of charge placed on the capacitor. Now capacitance depends on the dielectric constant that is in between the 2 metal plates. It also has this constant, which represents the permittivity of free space, and also it depends on the area of the plates and the separation distance. So if you increase the area of the metal plate, you can increase the capacitance. Now, if you decrease the distance between the two metal plates, if you bring them closer to each other, you can also increase the capacitance. The third way to increase the capacitance is to use a dielectric material. If you increase the K value, C will increase as well. Different materials have different dielectric constants. So for instance, air has a dielectric constant approximately about 1. It's like 1.0006 or something like that, but you could round it to 1. Paper, it can vary. The dielectric constant of paper could be anywhere between 3 to 8. And for water, the dielectric constant is about 80. And so different materials have different K values. And so those are the three ways in which you can adjust the capacitance of a capacitor. So you can increase the area to increase the capacitance, you could decrease the separation distance, or you can insert a material with a higher dielectric constant, and that will increase the capacitance. Now there are some other equations that you may want to write down when dealing with capacitors. Sometimes you need to calculate the potential energy stored in a capacitor, represented by the capital U symbol, and it's equal to 1/2 CV squared. There are some other forms of this equation. Another one is 1/2 QV, and another form is 1/2 Q squared over C. The one that I typically use the most is this one. And then sometimes I may use this if I have the charge. I rarely use this form. The last equation that you need to know is the energy density stored in the electric field of a capacitor. And it's basically the energy stored divided by the volume. And it simplifies to this equation. So it's 1/2 times the permittivity of free space times the square of the electric field inside the capacitor. And this constant is equal to 8.85 times 10 to the negative 12. Let's talk about electric current. When you hear the word electric current, what do you think of? I think of electricity, the movement of electric charge. Electric current is represented by the symbol I, and it represents the rate at which electric charge flows in a circuit or in a wire. And so I is equal to Q divided by T. The unit for electric current is amperes or amps. So 1 amp represents the flow of 1 coulomb of charge per 1 second. So let's say if we have 50 coulombs of charge flowing in a circuit every 10 seconds. So the current will be 5 amps, 50 divided by 10. So a current of 8 amps would mean that there's 8 coulombs of charge flowing every second. In a period of 2 seconds, 16 coulombs of electric charge will have passed any given point in the circuit. And so hopefully this helps you to see the relationship between electric current, charge, and time. So here's a problem for you. Let's say if we have a battery and it's connected across a light bulb. And let's say an average of 3 amps of current flows in a circuit to light up this light bulb. How much charge will have passed through this light bulb in a period of 5 minutes? And so we need to calculate Q, and also during this time period, how many electrons flow through the circuit during this time. So go ahead and find the answer. So first let's calculate Q. Now we know that I is equal to Q over T. So Q is equal to I times T. But we need to convert T from minutes to seconds. So let's do that. So we have 5 minutes and there's 60 seconds per minute. And so T is going to be 5 times 60, which is 300 seconds. Now keep in mind, 3 amps is the same as 3 coulombs flowing per second. So using the formula Q equals IT, we have a current of 3 amps or 3 coulombs per second, and we're going to multiply it by 300 seconds. So notice that the unit seconds will cancel, giving us the unit coulombs. So 3 times 300 is 900. So Q is equal to 900 coulombs. That's the answer for the first part of the problem. So the total charge that passed through this circuit is 900 coulombs in a time period of 5 minutes. Now, how many electrons pass through the circuit in 5 minutes? How can we get that answer? Now, once you have the charge, you could easily find the number of electrons. Remember, Q, which represents electric charge, it represents the quantity of charged particles. And all we need to do is convert it. So keep in mind the charge of one electron is 1.6 times 10 to the negative 19 coulombs. And we don't need to worry about the sign since we're focused on calculating the number of electrons. So the unit coulombs will cancel. And so it's going to be 900 divided by 1.6 times 10 to the negative 19. And so this is going to give us 5.625 times 10 to the 21 electrons. So anytime you hear the word electric charge, just know that it represents the quantity of protons or electrons, or basically the quantity of charged particles. Now let's talk about Ohm's law. What is Ohm's law? Ohm's law describes the relationship between voltage, current, and something called resistance. And the formula that goes with Ohm's law is this: V equals IR. Voltage equals current multiplied by resistance. And a resistor can limit the amount of current flowing in a circuit per given voltage. And so a resistor resists the flow of electric charge. Let's say if we have a battery connected across a resistor. And let's say we have a 20-volt battery, and let's say this is a 4-ohm resistor. So here is the positive terminal of the battery, here is the negative terminal of the battery. Now, electrons flow from the negative terminal of the battery to the positive terminal of the battery. So in this case, they're flowing counterclockwise in a circuit. But when dealing with circuits, typically you're going to be dealing with something called conventional current, which describes the flow of positive charge, which is opposite to the direction of electron flow, which is based on negative charges. So conventional current, represented by the symbol I, will show the flow of charge from the positive terminal of the battery, which is from high potential, to low potential. So current always flows from high potential to low potential. Make sure you understand that. And so that's why we use conventional current, but electron flow is opposite to the direction of conventional current. And this is really what's happening in a circuit. So just keep that in mind. Using Ohm's law, what is the current flowing in the circuit if we apply a voltage of 20 volts across a 4-ohm resistor? What is the current? So V is 20, we're looking for I, and R is 4 ohms. So ohm, which is represented by the omega symbol, that's the unit for resistance. And to get I by itself, we just need to divide both sides by 4. And so 20 divided by 4 is 5. So the current flowing in a circuit is 5 amps. Now, how much power is consumed by this resistor? To find the power dissipated by the resistor, you could use this equation, I squared R. So the current flowing in a resistor is 5 amps, and the value of the resistor is 4. 5 squared is 25. 25 times 4 is 100. And the unit for power is the watt. So this resistor dissipates 100 watts of power. Now power is the rate at which energy flows. So it's energy divided by time. So a power of 1 watt means that 1 joule of energy is being transferred every second. So in this case, the resistor dissipates 100 watts of energy. That means that it's converting 100 joules of electric energy to thermal energy or heat every second. Now let's work on some more examples that will help you to understand the concept of Ohm's law in relation to voltage and electric potential. Let's say if we have a resistor, and let's call this point A and point B. And we have a current of 5 amps flowing through the resistor. And let's say it's an 8 ohm resistor. What is the voltage across the resistor? So the voltage, which let's write it as delta V, based on Ohm's law, is equal to IR. The current is 5 amps. The resistance is 8 ohms. 5 times 8 is 40. So the voltage across points A and B is 40 volts. Now, let's say the electric potential at A is 70 volts. What is the electric potential at B? Now remember, the current flows from a high potential value to a low electric potential value. So B has to be lower than A because the current is flowing towards B. And we have the potential difference between A and B, which is 40. So B has to be 40 volts lower than A. So the electric potential at B is 30. So the voltage simply tells you the difference in the electric potential between those 2 points. It doesn't give you the exact numbers, only the difference. To find the other number, you need a starting value. Now let's work on another example. So let's say we have this resistor. It's a 4 ohm resistor, and we have a current of 6 amps flowing through it. And let's call this point A and point B. Let's say the electric potential at point A is, actually at point B, let's say it's 12 volts. What is the electric potential at point A? So first, just like before, we need to calculate the voltage. The current flowing through the resistor is 6 amps. The resistance is 4 ohms. 6 times 4 is 24. So we have a voltage of 24 volts. Now, to find the potential at A, we either need to add 24 to 12 or subtract 12 by 24. Which one is it? So the direction of the current will tell us what to do. It always flows from a high potential value to a low potential value. So because the electric potential at point A has to be higher than point B, we need to add 24 to 12. So this is going to be 36 volts. So that can help you to calculate the electric potential at any given point if you have the electric potential at the other point across a resistor. Let's try one more example. So let's say this is point A and this is point B. And we have a current of 3 amps flowing through a 5 ohm resistor from point A to point B. Now let's say that the electric potential at point A is negative. It's negative 12. What is the electric potential at point B? Using Ohm's law, we know that V equals IR. So if we multiply the current by the resistance, 3 times 5, that will give us a voltage of 15. Now, which point has the higher electric potential value? Is it A or B? The current always points to the low electric potential value. So that means that VB has to be less than VA. So current always flows from a high electric potential value to a low electric potential value. So what should we do? Will our answer be negative 12 plus 15 or negative 12 minus 15? If we add 15, that will give us 3. If we subtract by 15, it will give us negative 27. Now, on a number line, 3 is greater than negative 12, so it can't be 3. Therefore, the electric potential at point B has to be negative 27 volts because it's lower than negative 12 on a number line. Now, let's talk about series circuits and parallel circuits. What's the difference? Resistors connected in series only have one path for the current to flow. In this case, the current can only flow in this one path. It can flow up or down, but there's only one path for it to flow. In a parallel circuit, the current has multiple paths in which it can flow. So let's say the current is going in this direction. It can split off this way or that way. And so it has multiple paths in which it can flow. So here's a question for you. Are these two resistors connected in series or parallel? Is there one path for the current to flow, or are there multiple paths for the current to flow? In this case, there's only one path. So those resistors are connected in series. In this example, the resistors are connected parallel to each other because there's multiple paths by which the current can flow. It can flow through path A, through path B, or through path C. And so those resistors are connected in parallel. And so that's the difference between resistors being connected in series versus resistors being connected in parallel. Now, let's say if we have a battery and we have multiple resistors connected in series. So let's say this is a 3 ohm resistor and this is, let's say, a 5 ohm resistor, and here we have a 7 ohm resistor, and we have a 60 volt battery connected across those 3 resistors. What is the current flowing through each resistor, and what is the voltage across the 3 resistors connected in series? Now we know the current is going to flow in this direction, but how can we determine the current? The first thing you need to do when dealing with a series circuit is determine the equivalent resistance or the total resistance. And so the total resistance will simply be the sum of the 3 resistors. So it's going to be 3 plus 5, which is 8, plus 7. So the total resistance is 15. Next, you need to calculate the current in the circuit using Ohm's law, V equals IR. So we have a voltage of 60 volts across an equivalent resistor of 15 ohms. And 60 divided by 15 is 4. So the current flowing in the circuit is 4 amps. Now let's calculate the voltage across each resistor. And so let's call this R1, R2, and R3. So let's start with the voltage across R1. So we have a current of 4 amps flowing through it and a resistance of 3. So we could use Ohm's law, V equals IR. So V1 is going to equal I times R1. And that's a current of 4 amps times a resistance of 3 ohms. So we're going to have 12 volts across R1. Now, let's do the same thing for the second resistor. So V2 is going to equal I times R2. And so we have a current of 4 amps times 5 ohms. And so that's going to give us a voltage of 20 volts. Now let's do the same thing for R3. V3 is I times R3. And so in a series circuit, the same current flows through all 3 resistors because there's only one path for the current to flow. So I is the same for all 3 resistors. R3 is 7. 4 times 7 is 28. So we got 28 volts across R3. Now, notice what happens if we add V1, V2, and V3. 12 plus 28 is 40. 40 plus 20 is 60. And that corresponds to the voltage of the battery. And this is related to Kirchhoff's voltage law, which states that the sum of all of the voltages around a closed loop adds up to 0. Now, 60 plus 60 doesn't add to 0. 60 plus 60 is 120. So the only way this could work if some of these values are negative and the others are positive. And one way I like to think about this is what each element in a circuit is contributing to the overall energy of the circuit. Now the battery is an energy source, and so it delivers power to the circuit. So therefore, I like to ascribe a positive value to the voltage of the battery because the battery is increasing the energy of the circuit. It's delivering power to it. The resistors, however, they're not producers, they're consumers, and so they consume energy from the circuit. And so I like to give it a negative value. Thus we have what is known as a voltage drop across a resistor. And so when you add positive 60 and negative 60, you get 0. So let's say let's ascribe points to the circuit. Let's call this point A. Let's say this is point B, point C, and point D. Let's say the electric potential at point A is 0 volts. As we travel this way to the circuit, the electric potential will be increased because the battery provides energy to the circuit. And so for going from negative to positive, that's an increase in potential. So at point B, the electric potential is higher than point A. It's 60 volts higher because that's the difference here. The positive side has to be the higher side. Now, this side is positive and this side is negative. When current flows through a resistor, it flows from a region of high potential to low potential. And so for R2, this side is positive and this side is negative. And this is for R3. Now let's travel around the circuit starting again from point A. So going from A to B through the battery, we have a voltage boost of 60 volts. So we go from 0 to 60. The battery provides a boost to the circuit. Now going from B to C through this resistor, we have a voltage drop of 28 volts. And so 60 minus 28 will give us a potential of 32. And so I'm going to put that here. So the potential at point C is 32 volts. At point B is 60 volts. Now going from point C to point D, we have another voltage drop of 20 volts. And so 32 minus 20 is 12. Now going from D to A, we have a voltage drop of 12 volts. And 12 minus 12 will bring us back to 0. And so that's the basic idea behind Kirchhoff's voltage law. As you travel around a closed loop, the sum of all of the voltages, the voltage boosts and the voltage drops, is going to be 0. Now the last example that I want to go over is a parallel circuit. Let's say we have a battery connected across 3 parallel resistors. And let's say it's a 12 volt battery. And this is a 2 ohm resistor Here we have a 3 ohm resistor, and here we have a 4 ohm resistor. What is the current flowing through each resistor? Now notice that each resistor is connected across the same battery. So the voltage across each resistor is the same, it's 12 volts. And so we could use V equals IR to find the current in each battery. So to find the current, let's say in R1, here's what we need to do. It's going to be the voltage of the battery divided by R1. So that's 12 divided by 2. And so we have a current of 6 amps flowing in that resistor. To find the current flowing through R2, which we'll call I2, it's going to be the voltage of the battery divided by R2. So it's 12 divided by 3. And that gives us a current of 4 amps. For the last one, I3, it's going to be V divided by R3. So 12 divided by 4 is 3. So we got a current of 3 amps flowing in this resistor. Now that means that we have 3 amps of current flowing in this region and in this region as well. Now how much current is flowing in this region? Notice that if 3 went to the right and 4 amps went down, then 7 amps of current has to enter this region. And that's the basic idea behind Kirchhoff's current law. The total current entering a junction, let's say at this point, is equal to the total current leaving that junction, which is 3 plus 4, and that's 7. And so that's Kirchhoff's current law. The total current going into something equals the total current leaving that something or that junction. So here we have 7 amps flowing to the right, 6 amps flowing down. That means that a total current of 13 amps must be leaving the battery. Now going to this section, we have 4 amps meeting up with the 3 amp current. So we have a total of 7 amps flowing in this region, which meets up with the 6 amp current. And so we have a total of 13 amps entering the battery. So hopefully this circuit helps you to see how current flows in a circuit and how it's related to Kirchhoff's current law. Now, let's calculate the total resistance or the equivalent resistance of the circuit using Ohm's law. If you know the total voltage of the battery and the total current leaving the battery, you can calculate the equivalent resistance of this circuit. You can view it as one big resistor. And so let's use Ohm's law to do that. The voltage is 12, the total current is 13, and let's calculate the total resistance. So it's going to be 12 divided by 13, which if we round it, that's 0.9231 ohms. Now the second way in which we can get that answer is by using a formula for parallel circuits. So the total resistance or the equivalent resistance of resistors in parallel is going to be 1 over R1 plus 1 over R2 plus 1 over R3 raised to the minus 1. So go ahead and type this in your calculator. Type in 1 over 2 plus 1 over 3 plus 1 over 4, all within a set of brackets, and then raise it to the negative 1 power. This will give you the same answer, 12 divided by 13, or 0.9231 ohms. So those are 2 different ways in which you can calculate the equivalent resistance of a parallel circuit. So I'm going to stop here, and for those of you who want more detailed videos on electric circuits, magnetism, or any other Physics 2 topic, feel free to check out my YouTube channel and look for my new physics video playlist, and you can find specific topics that you might be looking for. So thanks for watching.